Hello again, this is Tom from Every Step Calculus and EveryStepPhysics.com. We're going to do this problem here, changing from Cartesian coordinates to polar coordinates, and then do the double integrals on it to find the volume of this area here. It's really a three-dimensional, not a two-dimensional picture. And you buy my programs, and then you're instructed how to put this index 8 into here with the open and close parentheses, which tells the calculator you want to do a program. And let's do it. Index 8 to get to my main menu. I'm already at polar double integrals here to save time. Write this on your paper. This is the formula for volume with regard to polar coordinates. And remember that calculus and physics is all scored on partial credit in the class curve. In other words, you get points for whatever you can put down that's relative to the test problem, because the problems are so difficult, courses are so difficult. So make sure you write that down. In this case, where the order of integration is going to be dr first, we're going to do the radius section r1 and r2 first integrals, okay? But also write this down here. These are the formulas. X squared plus y squared is always equal to r squared, okay? Remember that in polar. If you see it, notice these are all setup problems, pathetic setup problems. Calculus, after 30 years of studying this stuff, I've never found one problem, not one problem that's useful that calculus solves. Not one. And I have 20,000 sheets, because when I program this, I have to put them down on a sheet of paper first, figure out the correct way of doing the problem, which corresponds to different professors, how they do it, what characters they use, etc. Come up with the best step-by-step process, and then I can program the calculator to do those steps, okay? So write this down here. X is equal to r times cosine of theta, y is equal to r times sine of theta. When you're changing, anytime you see a y, you're going to change it to this. And of course, r squared is equal to x squared plus y squared. Here's the order of integrations. This is the region. And so write this on the columns, you know, side of your paper of the test problem. Press enter. We're going to enter the function now. You have to press alpha first before you enter anything in these entry lines here. So I've done that. We're going to put the radical sign in second. And here's the time sign second area. Here's the radical sign here with a left parentheses. We're going to put another left parentheses in here. We're going to add x squared plus y squared. Put in the right parentheses to the third power, and then put the right parentheses to close out the integral. The calculator changes it to this, which is true. But technically you're going to change this to r squared, and it turns out to be really r cubed when you do the calculations, you know. So change the polar, z equals to r cubed. These are all setup problems. You can just see x squared plus y squared. It's in a lot of problems for polar, because these are setup problems to make it look like they solve something useful, and they don't. And of course the professor is up there making you think that, oh my God, this is so important in your life. It's the basis of all mathematics and everything else. Baloney, baloney. It's like taking 3 semesters of Sudoku problems or crossword puzzles. Extremely difficult, but at the end you've wasted your time. You have done nothing, except if you like to do that, you can use it for entertainment while you're waiting for a plane to Phoenix. Z equals r cubed, okay, so that's the, and we're going to use the, you can do either one of these, but I have it set up to do different order of integration, but we're going to use number one here, dr to d theta. And again, the volume formula, write that down. And we're going to enter the limits, and the limits here are for r is going to be 9 minus x squared. Notice that the difference of squares, so you have x 3 plus x when you factor this out, and 3 minus x. So the upper limit is going to be 3 here. The lower limit is 0. So let's do that. Alpha 0 for the R11 and alpha 3 for the upper. Difference of squares is a big deal in calculus, so remember that. Anytime you see x squared minus, like here, 9 minus x squared, this is a square and this is a square, so it's, you factor it out, x plus, 3 plus x and 3 minus x. And that way, when you compute it out, it's going to be, the upper limit is going to be 3. It always happens like that, so make sure you learn that. You say it's okay, and the bottom one is since you're making this circular over 1/2 of a circle, it's pi over 2 for the outside limit, and 0. You're starting at 0 here, and when you go 1/2 of a circle, it's pi over 2. When you go all the way around a circle, it's 2 pi. So the bottom limit is alpha 0, and the upper limit is alpha second here pi divided by 2. Say it's okay. You always can change it if you want. I give you that option when you're entering anything into the entry lines. So here it's set up 0 over pi over 2, and the first one is r, dr, so that's 0 over 3. We have to multiply times r first, so it becomes r4. And the double integral becomes r4 dr d theta with these limits. Integrate with respect to r. Turns out to be r5 over 5. Limits of 3 and 0. And r2 is equal to 3. This equals 243 over 5. At r1 equals 0. dr equals 0. Upper minus lower, 243 over 5. Okay? That becomes a new integral for theta. So write that on your paper, of course. We're going to integrate with respect to theta. Turns out to be 243 theta over 5. And with these limits, that theta 2 over pi over 2 turns out to be 243 pi over 10. And 0 is equals 0. Upper minus lower. And the answer is 243 pi over 10, or 76.3 cubic units. Pretty neat, huh? EveryStepCalculus.com, EveryStepPhysics.com. Go to my site, buy my programs, and pass calculus. Plus, you get my help. You can call me on the phone if you want, or you can email me your tests, problems. I'll show you how my programs work on your little quizzes or tests that you get before you have finals tests and stuff like that. So understand it's quite a service when you buy my programs, okay? So anyways, have a good one. Good luck in your class.